Hey, we have talked about graphing motion. We've talked about graphing distance versus time, velocity versus time, and acceleration versus time. Now we're going to talk about plugging some of that knowledge into equations to figure things out. And these equations are called informally NIB Suvat equations because that's not an acronym, it's not a mnemonic or anything like that. Those are the actual variables that we use in the equations. And I'm going to tell you exactly what they stand for and then how we use them. So let me bring this up. Oops, wrong one. There we go. All right, so let's talk about these things. The S is very intuitive. S stands for distance. Distance or displacement, either one. Normally we're talking about displacement, but because we use signs plus and minus in the equations, the direction is pretty much implied by the sign, whether it's a positive or a negative. Now, I'm not sure why we use S. This is not just an IB thing to use S for distance, but usually you'll see distance represented by the letter D. That's just the way IB does it. Other people do it with S too, but that's why you might see it two different ways if you're taking a different kind of physics course. Of course, that really ruins the word that we've created here. U is initial velocity. Okay, so this is the velocity that the object was going when you start using the equation. A lot of times it could be from starting from 0 or whatever. We'll talk about that. But it's the velocity this was going when you started measuring it. This is something that other physics label V sub I for initial velocity, initial velocity. Okay, velocity, or V, is final velocity. Something that other physics courses label V sub F. None of these are wrong. It's just this, I'm letting you know what standard IB uses and what standard other people use. And I kind of like the IB way because it makes things very easy to remember, as I'll show you when we get more into this talking about the equations. But it's the final velocity. When you are done measuring at the end of the time that you're doing this, that is what that velocity is. And of course, things don't always speed up, they can slow down. So V could be smaller than U. It just depends on how it works out. Of course, A is acceleration. And in other physics, this one's pretty hard to figure out, but in other physics, it's also labeled A. It just makes sense. All right, so, and finally, there is time. Time, or T, is for time. Obviously, other places label it as T. All right, so there are some things that I need you to remember about all of this. Number one, keep this in mind. Suvat is in such a way, this is such a word that you can remember this every problem that you have, and that's good because I'll show you how we're going to use that. There are some things that you also need to remember for this, in that just when you think about this, if you have a constant velocity throughout the entire time That's your working, that equation that you're using is measuring the motion. If you have a constant velocity, of course, u equals v. All right, so that means no acceleration. All right, because it's constant. So though, if you have a problem that says under constant velocity, you already know 3 variables, as long as they give you what that velocity was. Okay, if you see or read the word or hear the word rest in association with these things, that means 0 velocity. They are not, it is not moving. 0 acceleration, 0 velocity. It is starting out. See, when it, if you state that it is moving from rest, it means u equals 0. If you are slowing down to rest or some form of either one of these, right, then final velocity is going to equal 0. And I make my zeros like this to distinguish them from O. That can get confusing. I've had students get upset that I put that line through there because they're not used to it. I don't know. I've done it ever since I was in high school, and sometimes it does help me to know the difference between an O and a 0. Okay, I also want to cover something with you. I want to tell you that there is another word for this, and that's kinematics. This is the formal word, or we could say kinematic equations. So informally in IB we call them Suvat. Formally in all of physics they are known as the kinematic equations. And this is kind of an interesting history to this that I think. The kinematic comes from the Greek word kinema, meaning motion, which is exactly what these equations are about, is motion. And when you add the word ATIC or TIC to the end of a word, now this is an adverb, or I'm sorry, this is a verb, meaning an action word, motion, action word, right, in the Greek language. But if you take and add an attic or a tick to the end of it, you turn it into an adjective, which means it's describing a motion. I'm sorry, describing a noun. So equations is a noun, and kinematic is the adjective describing these equations. These equations are about motion. Okay, and that's really all that is about where this word means, what it means. Whenever you see kinematic, think of motion. As a matter of fact, there's another word that comes from exactly the same root, same root word, kinema, and has the attic at the end. That means motion, but we pronounce it completely different, and that's cinema or cinematic, which is the old term for movies, right? So whenever you wanted to go to a movie, we changed this verb into a noun and called it a cinema. But there you go. That's exactly the same word. And you can now see the similarities. It's moving pictures, and this is moving objects. And so they're exactly the same word. All right. Where do these equations come from? What are they? How do we use them? And so forth. Okay, well, what I'm going to do, there are 5 equations. We only use 4 of them. They are in your data booklet. Even though I'm deriving them, you don't have to. I just want you to see where they come from, how legitimate they are for what we have them do, and show you that you can derive equations in physics, that you, not me, you can derive equations. Because even though you're not going to be required to derive these kinematic equations, you will be required on a test in a lot of cases, to derive one or two equations based on your knowledge. Now, I can't tell you what they are. I can't tell you what they're going to be because they're always different. You can actually go to websites where they list every equation that's ever been on an IB test that's not in the data booklet, and you can try to memorize those. Not a good idea. You can't do it. There could be hundreds of them. So what I'm going to show you here is kind of start showing you how to derive equations, and every once in a while you'll be called upon to try to do that so that you get used to it. But it's no guarantee that the ones I'm having you derive are the ones that'll be on the test. You're just going to have to go with it. The reason why IB does that is they want to make sure that you understand the concepts and can apply the concepts and can see the similarities or the relationships to the concepts. Okay, with all that, let's get started. We're going to be going from, on the wrong thing here, as usual. So what we're going to do, I'm going to draw a really bad graph here, and this is a velocity versus time graph, because velocity can tell us everything. It can tell us acceleration, right, from the slope, and from the area can tell us the distance. So everything that we need to know about motion is contained in a velocity versus time graph. All right, now notice in this case, this is velocity and this is time. In this case, because of the slope here, we have the initial velocity is equal to 0. But what if we started measuring this and the thing was already in motion and we had an initial velocity of not 0, something else? I'm trying to think of a good thing. We'll just say y, because this is the y-axis, right? So what if it was something that was non-zero? So it would start up here. All right, that'll come into play here in just a second. All right, so the first thing that we do know is we want to figure out acceleration, right? So acceleration is equal to what? It's the slope of this line. We're going to go with this green line. We're going to say the slope from here to here, down here to where the y-intercept is. So what is that? This is the initial velocity here, and this is the final velocity here, right? So because we started initial here, we ended up final there, and we know that acceleration is the change in velocity. It's the rate of change of velocity. So that's the rate of change. It's the delta v, change in velocity, over the change in time. Now from now on, I am just going to write the change in time as t. We're just going to know how many seconds that has ticked off, or however many microseconds or whatever it is that it is. We're just going to know that t is delta t. It always is. All right, so we're going to rewrite this equals final velocity minus initial velocity over time. Okay, that is acceleration. That is the slope of this line. Time is v minus u is the rise. T is the run, right? That's on that axis. The v's are on that axis. So there we have the slope. So we can rearrange this. We can make this AT, move the t up there, equals v minus u. And so we can then rearrange this. Of course, this can be rearranged in any way, but the way we do this in a formal manner, and this is our first kinematic equation, is like this. This is what you will see in your data booklet. V, final velocity, equals initial velocity plus the acceleration times the time. Okay, so there you go with our first kinematic equation. Now with the second one, we want to find out, let's see if we can find out what the distance is, right? So looking on here, if I draw this. I have two things I need to add up. I have a triangle and I have a rectangle. So the distance is going to equal the area of this rectangle, which is the basically, right, the initial velocity, this, because that's the distance from 0 to the initial velocity. So it's the initial velocity times the time. All right, and I have to add that to the area of the triangle, which is 1/2 1/2 of, now this is where it gets a little bit complicated. It's this right here. This is, I should put this, the V is right there. So it's right here. Now V is actually V minus U, right? That would be this value here. So V minus U is the size of this side of the triangle times the time. So that's 1/2 the base times the height, right? Which is the triangle. All right, so let's just work this out. S equals UT plus 1/2. Now here's a trick that is very common in physics. We have a value here, and in another equation that is related, that is directly related to this, we have a value for this that we can put in here. Equals 1/2 V minus U equals AT, right? Because we did it right there. We did AT times T. So our fourth kinematic equation is S equals UT plus 1/2 AT squared. Okay, pretty straightforward. Once you understand the trick is sometimes you have to find out two different things that are equal to each other and substitute them in. And I'll tell you the value of this when we're all done with this. Okay, so we have another thing. Let's combine these two things and see if we can come up with another equation. To do that, I want to rearrange the V equals U plus AT. Give me a second here. Put that back in order. Okay, V plus equals U plus AT. And I'm going to try to figure out what my time is. So AT equals V minus U, right? Same thing we had up there. And so T equals V minus U over A. Now we can take this and we can substitute it in for every T that we have here. Okay, I was going to say I can spill the tea, but I think my daughter would have a heart attack if I did. So I won't say anything about spilling the tea. All right, so let's substitute in there. S equals U times V minus U over A plus 1/2 times A times V minus U over A squared. Now this looks like a big mess, and it's going to get better because we're going to really mess this up. All right, so I'm going to take and I'm going to separate out the A. We got A in both of these, right? Let me make sure I'm doing this right. Okay, so S equals U over A, I can just bring that A out there, times V minus U, plus 1/2 A over A squared times v squared minus uv plus u squared, right? That's what that is squared. And I brought the a squared out here. I can cross out that a, so I end up with 1 over a. So this is basically 1 over 2a. I got 1 over a on both of these, so I can take those out. Equals 1 over a times u times v minus u. Isn't this a pretty little picture here? 1 over 2a times v squared minus uv plus u squared. All right, and I can take and I can bring this a out of both and multiply it the other side. So as equals u times v minus u plus 1/2 v squared minus uv plus u squared. This is we're kind of getting close here, so hang in there. As equals uv minus u squared plus 1/2 v squared minus 1/2 uv plus 1/2 u squared. I'm going to run out of room here, but as equals, all right, so let's go with the u squareds here. U squared minus u squared plus 1/2 u squared equals minus 1/2 u squared. uv minus 1/2 of u, I'm sorry, let's see, minus, yeah, minus, so uv minus 1/2 equals plus 1/2 uv, and then 1/2 v squared is plus 1/2 v squared. If I got that right. Let's see. Yep, I've got that right. Now then, because I've got the halves on all of these, I can move it to the other side. 2as equals u squared plus uv plus v squared. Guess what? 2as equals u. I'm supposed to get that right. It should be minus u squared. Let me fix that. Right? It's minus u squared. Yeah. All right. I can easily fix that. Minus u squared. So that comes out to, sorry, let me get this, I want to straighten this up and make sure I get this right. All right, so what I actually get, if I rearrange this to v squared plus uv minus u squared, I will get v squared minus u squared. Yes. Okay. Now then, with this, I can rearrange this, and it gives me v squared equals u squared plus 2as. Just move this over to that side, and there is our third kinematic equation. Now that one was kind of a bear. That was really something to get to, but we have a very useful equation here that you can make use of whenever you need to. So that's good. All right. For our fourth kinematic equation, let's start out. We're going to go back to this equation here and this equation here. Let's see, this equation here. And we're going to say, since a equals v minus u over t, we're just going to substitute that in here. So s equals, and this is not going to be nearly as bad as the one we just did, trust me, equals ut plus 1/2 v minus u over t, because that's what a is, times t squared. Now immediately we can get rid of the t squared because these two cancel out, right? So we have 1/2 v minus u, I'm just going to write it out so it's clear, ut plus 1/2 v minus u times t. S equals ut plus 1/2 v, be vt, minus 1/2 ut. And so S equals ut minus 1/2 of ut equals 1/2 ut plus 1/2 vt. 2s equals ut plus vt, and it should be, let's see, do I want to do that? Nope, sorry. We could do it this way. There is no right or wrong way to derive these equations or end up with a specific equation as long as you follow the proper algebra rules. I'm trying to get to the ones that are in your data booklet and the ones that we use the most. So S equals 1/2 of, let's see, 1/2 times v plus u times t. And I can just put this into a very simple v plus u over 2 times t. That is your fourth kinematic equation. Okay, so you see these listed, let's see, 1, 2, 3, 4. You see them all listed in your data booklet, and I'm going to show you how to use these now that you've seen them derived. If you didn't follow exactly what I did to derive them, that's okay. You could watch this over and over again 2 or 3 times, and I think you'll get it. It'll make a lot of sense if you watch this portion over and over again, 2, 3 times. It's not that difficult. It looks very difficult because there's a lot of stuff taken up, a lot of variables on there and all this stuff. But really, when it comes down to it, it's just adding, dividing, and mostly adding and multiplying and things, but mostly adding and subtracting, and it's not that bad. All right, so make sure you understand how to do that, because you will be called upon to do things like that. I'll give you some practice on some other things, and I just want you to see how to do it on these. Okay. All right, so how do you use these? Here's a sample problem. I've written the equations here so you can easily reference them as I go along. All right. I always think I'd take care of that. But, all right, a particle is accelerated uniformly from rest so that after 10 seconds it has achieved a speed of 15 meters per second. Find its acceleration and the distance it has covered. All right, so how the heck do we do this? Here's how you must do this. You must do this. This is not an option. I'll just write this out. Then I'm going to admonish you because I know what you're going to want to do. And if you're wise, you will listen to me. But here we go. All right. Write down vertically like this, Suvat. Okay? And then you fill in things you know and things you don't know. So reading this again, a particle is accelerated uniformly from rest. So we know that from rest means the initial velocity is 0 meters per second. So that after 10 seconds, time equals 10 seconds. It has achieved a speed of 15 meters per second, so final velocity is 15 meters per second. Find its acceleration. We do not know that. And we do not know its distance because they want us to find that. Now here's the beauty of the kinematic equations. We have 3 variables, and so we can figure out the other 2 variables using these equations. You only need 3 variables to figure out any of the other 2 variables that they may be asking for. So as long as you've got 3, you're given. Now, obviously there's not 3 numbers up here. It's 10 and 15, but they give us from rest, and that always means 0. So this is basically 0, right? Okay. Now then, the importance of writing Suvat is so that you can keep all of this straight. Things can get very complicated in these problems. This is a very simple, straightforward problem. And if you take the few seconds it takes to write out Suvat and fill in this little information here, it will actually save you a lot of time and make doing the problem a lot easier because you've got listed right here everything that you need to know. Almost. There's one more thing you need to do. You need to figure out what equation are you going to use to figure out what you want to know. So they ask for what is acceleration? Okay, well, let's figure out what's acceleration. Which one of these equations up here has u, v, a, and t in it, but not s? So that we can use these 3 things and figure it out. We can't figure it out what s is, and we don't know what that is yet. All right, so right here at the very top, u, v, a, t, right there. Very, very straightforward. We can't use this one. This one has u, t, and a in it, but it doesn't have, it has s. We can't use that. This one has s. We can't use that. This one has s, so we can't use that. That may come in handy for the second part where it wants us to cover the distance. Okay, so what is the equation that we use? Write it down. That way you don't have to keep looking back. Once you've discovered it, why take time to look back at your data booklet more than one time to work on this equation? Just go ahead and write it down. And there you've got, excuse me, there you've got all the information that you need right there in front of you. Very easy to access. All right, so we want to do the acceleration, and we need to work on that. So AT, we need to get this equation to where it works for us. A equals v minus u over t, which is an equation you probably know in your head because that's what acceleration is, right? The rate of change of velocity. But it really helps to work through this process so that in the pressure of taking the test, and if you take your time and do this, you will know that you're getting things set up correctly. And I am one who uses this kind of thing all the time because when I'm taking a test, I get to thinking ahead. I get to thinking about past problems. Did I do this on that problem while I'm working on this one? And I will do something silly, like I'll put a plus sign here, or I will leave off the T or something like that, and it'll just blow right by me because I'm not fully concentrating on this problem in the course of taking the test. So do what I say. Write down Suvat, fill it in, write down the equation, and then figure out how you need to manipulate that equation to use it. All right, now it's just a matter of plugging it in. Our initial velocity is 15 meters per second minus 0 over the time of 10 seconds. And so our acceleration, 15 divided by 10, acceleration is 1.5 meters per second squared. Now, do we have the right units? If we have the right units, we have gone a long way to solving this, to knowing that we solved this correctly. 15 meters per second divided by 10 seconds. Obviously, this comes down here, and that becomes meters per second squared. So that works out, all right? Check the units, make sure they make sense. All right. Now, let's work on finding the distance. So we've got all kinds of choices here. Now, I suggest you do not use the acceleration, anything with the accelerator, because you've calculated it. What if you made a mistake in here and you got the wrong acceleration? That means you're going to get the wrong answer here. And trust me, IB will not forgive you for that. So don't go with the acceleration because you didn't have it at the beginning, and on the off chance that you made a mistake, go with the equation that has S, U, V, and T in it, S, U, V, and T, so that you can go with that. So that means this one right here. So S equals, and you write it down, of course, V plus U over 2 times T. So now we just fill it in. V is 15 plus 0 over 2 times 10 seconds. So that is going to be S equals 7.5 times 10. S equals 75 meters. And does that make sense? We got 7.5 meters per second, M per second, times seconds, so which is plus 1. So those cancel out. They had 1 minus 1 is 0, and we end up with just meters, and so there is our answer. Now, you won't always have time on a test to verify that things are correct, but let's see if they are. We know that our final velocity is 15 meters per second. Let's find something that has both acceleration and distance in it, and that would be this one. And let's see if we come up with the right answer. So V squared equals U squared plus 2AS, which means V is square root of U plus 2AS, and that equals the square root of 0 plus 2 times acceleration is 1.5 times velocity is 75, and that equals the square root 2. Well, we actually don't even need our calculator for this. 2 times 1.5 is 3. 75 plus 75 is 150, plus 75 is 225. And guess what the square root of 225 is? It's 15. So because that worked out, we know that we got the right two answers. Now, like I said, you won't always be able to double check on a test like this, but if you can, that really helps to make sure you got a right answer. So sometimes when I see people going over their test for the third or fourth time to make sure they got everything right, I don't see them doing things like this. I see them trying to go over all of these equations again to make sure they got it right. Whereas if they just did one more equation instead of two, then they would know that it was right. Okay, so just keep that in mind. All right, let's do a little bit harder problem here. All right, now this one is going to take a while, and you'll see why here in just a little bit. All right, we've got a train that travels along a straight piece of track between two stations A and B. And a lot of times it really helps to draw a picture. All right, so there's station A, station B. The train starts from rest at A. So at A, we'll write this down in a minute because I want to point something out to you. Starts from rest at A and accelerates at 1.25 meters per second until it reaches 20 meters per second. So at some point it reaches 20 meters per second, and then it travels at a constant velocity. It says speed, but constant velocity for a distance of 1560 meters, and then it decelerates at 2 meters per second to come to a rest at B. All right, so we have three segments here, okay? We'll call this 1, 2, and 3. And that means we need to write down Suvat for segment 1, segment 2, and segment 3. Suvat, Suvat, Suvat. All right, so in the first segment, we don't know what the distance is. Initial velocity was 0. Final velocity was 20 meters per second. And the acceleration was 1.25 meters per second squared. And we don't know how much time it took. At the second one, we know the distance is 1,560 meters. Its initial velocity is 20 meters per second. Final velocity was 20 meters per second. And that tells us that acceleration was 0, right? And again, we have no idea of the time. Finally, segment 3, where it starts decelerating, so this train got up to speed, traveled at that speed for a while, and then slowed down to come to the second station. We don't know what that final distance is. Its initial velocity, 20 meters per second. That's what it was doing when it started this particular segment. Final velocity, it came to rest. See, to come to rest at B is 0. Acceleration, 1.25 meters per second squared. And the time, who knows? They didn't tell us. So they want to know what the distance from A to B is. So we only have one distance here, so we have to figure out the distance here. So S equals, which one has U, V, and A in it? Well, U, V, but not S. U, no V. Well, it's right here. It's this bottom one. S equals V plus U over T. Nope, sorry, not that one, because it's got time. Do not be ashamed if you pick the wrong one and you have to start over. It happens, all right? So what we actually have, see, we want U, V, A, and S, because we want the total distance. So U, V, A, and S. And that is, as far as I know, the only one we've got. So V squared equals U squared plus 2AS. S is going to equal V squared minus U squared over 2A equals U squared is 0 squared, excuse me, plus 20 squared over 2 times 2.0. Right? I'm sorry, 2 times, I'm getting ahead of myself. That is the third segment, acceleration. So it is 1.25. All right, I want to make sure I come over here and get my numbers right as I do this. Okay. Okay, so that is going to be 400 divided by 2.50. And so S is going to equal 160 meters. Okay. All right, so that is segment 1. What we're trying to find is the total distance. And so that's add segment 1 plus segment 2 plus segment 3. Fortunately for segment 2, we have the answer already. So for segment 3, guess what? We've got the same numbers that we had for this one. So S is going to equal V squared minus U squared over 2A. is going to be 0 plus 20 squared over, and see, this is where writing all this down makes sense. I wrote down the wrong number there. You guys probably caught that when I first did it and said, hey, that's not right, which is great, but it should be 2.0. And it doesn't say 2.0 here, but we're going to assume that. That is a pretty bad way to write that. All right, 20 squared over 2 times 2.0, and it's going to be 400 divided by 4 equals 100 meters. So ST equals segment 1, 160 meters, plus 1,560 meters from segment 2, plus 100 meters from segment 3. If you add that all up, you get 1,820 meters. That is the total distance. So I'm going to write that up here. I'm going to make that red. S equals, S total equals 1,820 meters. Now, let me erase all of this so I have some room. And don't worry, you can go back to this part of the video and recover it and watch me do it all over again. But if you follow along, you should be able to figure out very quickly. You just find the right equation, manipulate it to get the variable you want if you have to, and then just plug and chug. All right. Okay, so we want to find now the total time it took for the journey. So now we've got U, V, A, and T. U, V, A, and T. Very nice. So time, what is going on here? Give me a minute here. I seem, nope, don't want to do that one. That was my old problem. Why? Oh, I see what I'm doing. I'm erasing. I didn't change my eraser to my pen. Okay, so we want to use this. So time is equal to V minus U over A. We worked that out when we derived equations, right? So fill that in, equals 20 minus 0 over 1.25. So the time it took let's see here, time it took was 16 seconds. Okay, easy enough. Now, we've got the same numbers over here. We do this exactly the same way over here. So on segment 3, so let's go ahead and figure that out. T equals V minus U over A equals 20 minus 0. I have to do my zeros. Divided by 2.0, and that's going to be 10 seconds, right? 20 divided by 2 is 10 seconds. All right, over here we need to use a different equation. We don't have acceleration, so we have to find S, U, V, and T. S, U, V, and T. So T equals 2S over V plus U. Right. Yeah, over V plus U. Let me make sure I did that right. Okay, so T equals 2 times 1,560 divided by 20 plus 20. All right, they're equal, they're the same. So the time is equal to, when you multiply all that out, comes out to 78 seconds. So when you add it up, time total equals 16 seconds plus 78 seconds plus 10 seconds equals 104. This was a very short trip. 104 seconds, not even 2 minutes. This was very short. But that's okay, because we're just learning how to do the problem. We don't have to figure out if it's realistic or not. All right, so I'm going to write that up here. Total time equals 18. Total time equals 104 seconds. Now, very easily it says, what's the average speed for the journey? Average speed is the time it took, the velocity they took for the entire journey over the entire time. So we're going to write it like this. That's not final velocity in this case. Well, we'll just V average equals 1,820 meters divided by 104 seconds. And that is going to give us an average velocity over this entirely hugely long 104-second trip of 7.5 meters per second. Okay, so that is how you apply this. Sometimes you have to break things up, draw pictures if you need to, and if there's any kind of complication, draw the picture. Even if there isn't, draw the picture just to be sure. Understand what you're going to have to do. Break these up into segments. You're going to have to add things up if they want the total. Or they may ask what happened during segment 1, what happened during segment 3, whatever they can ask. There's a large number of things they could ask on a question like this. Okay, so that is Suvat, or formerly kinematic equations, how to use them, how to derive them, which you don't have to do, but know how to derive things, other things. When we get there, be ready to be able to do that. And how to use them in an equation for an example. Now, I know this is a really long video and there's a lot here, but I have some problems that I want you to work, and do the best you can to answer all of them, but definitely bring them with you to class if you have any questions. If you don't, bring them to class, because some of your classmates may have questions and you can work on it together. Or you can ask me questions. But we'll cover some other things in class about this as well. So good luck with those questions, and I'll see you in class.